Hey, welcome to a lecture on the inputs for GLHEPRO, specifically the loads that we input. I guess it can be a little bit confusing, so I hope to shed some light on it in this lecture. So this is an outline for what we plan to cover. Um, and in terms of goals, right, I'd like to introduce you to how heating and cooling loads are used in GLHEPRO, how and why we represent them in the what we call the hybrid time step format. Um, there's two types of loads. There's loads on the heat pump and then what we call direct loads on the ground heat exchanger. So we'll discuss those. Uh, what types of loads should be input? We'll look a little bit at the characteristics of the loads. Right? And these loads often are derived or determined with a whole building energy simulation tool like Energy Plus or eQuest or something, something like that. And the goal of this lecture is not to teach you how to use Energy Plus or other hourly simulation tools. That's probably a whole semester course in and of itself. Okay, so first question is, why do we use all these loads, right? Um, conventional equipment's often sized with a peak load, either from a single cooling design day or from monthly cooling design days. Um, Even though it's often done with a single cooling design day, it's also true that there can be situations where the peak cooling load for a zone uh, does not occur on the hottest day of the year in July or August. Instead, it may occur in the winter months. An example of that would be a hotel room that faces south in a climate like Atlanta, Dallas, Oklahoma City, Stillwater, Oklahoma, where we have some days in the winter can be relatively warm. Say it's not unusual in any of those locations to have a day where the temperature exceeds 68 Fahrenheit or 20 degrees Celsius. And on that day, if it's sunny, we can certainly have the peak then because the solar radiation, since the sun's lower in the sky, we have a higher solar irradiation, higher BTUs per hour per square foot or watts per meter squared in the winter. So that's kind of an aside, but in any case, we often then just make our equipment selection based on that. When we come to the ground heat exchanger, we have a different problem though. The ground has a very long time constant. Right? So the exiting fluid temperature coming from the ground, right, depends on the current load. Right? And if that was all it was dependent on, then it would be more or less like the conventional equipment sizing. But it also depends on the loads in the past, the recent loads and the distant loads. So the loads for the last few hours, the day before, the days before that, and so on, they can all impact what the temperature is. And furthermore, loads from even more than a year ago are important particularly when the loads are imbalanced and when there is significant borehole interference. So not so important if the loads are perfectly balanced over the year, then we don't expect to have a significant effect of loads from more than a year ago. But if they have, say, moderate to significant or moderate to large imbalance, then the temperature will tend to build up over time or draw down over time, depending on if we have excess of heat extraction or excess of heat rejection. All right, and also, this is more important cases where there's significant borehole interference. So you won't see this so much in, say, residential systems with 1 or 2 or 3 boreholes. It becomes more important as you get more and more boreholes, the possibility for them interfering with each other uh, is higher. So it becomes more important in those cases. Now, this multi-year effect, right? And by this specifically, I mean where we have long-term temperature buildup or drawdown that tends to drive the size. Surprisingly, is controversial in some circles. My own reading of the situation, my own opinion, is that there's some misinformation being spread by some people, and it's fed by limited experience. So, if you've only worked on or looked at buildings where the loads are relatively, heating and cooling are similar over the year, or buildings where the boreholes, there's not that many boreholes, or the boreholes are quite spread out, then it's likely to look like this. There's not likely to be a long-term temperature effect. Okay, and there's a lot of buildings like that where it's really not important. It is based on the physics of conduction heat transfer, right? And I mean pure conduction, not with groundwater flow and so on. So, for example, if you have high groundwater velocities, those are rare, but when they happen, they can affect long-term heat buildup. So there's a paper, should be listed in the reference section, by Andrew Chason et al. On this subject of the effects of groundwater velocity, and looks at different geological situations where you have different hydraulic conductivities and different groundwater head gradients. So usually get high groundwater velocities, you need a highly conductive ground and a high head differential. So you might get that, say, if you're, well, I suppose there's a couple cases. One is if you're near the mountains but you're on some kind of sand and gravel aquifer, so right if you're at the edge of the coast with a mountain range behind you, right, then you can have a significant groundwater flow. Another possibility, if you have say a sand and gravel aquifer and you're pumping water out of it, maybe not somebody's pumping water out of it and driving groundwater flow. So those can definitely have an effect, but they're probably not as common as some people think. There's also the possibility for percolation of rainwater. My own analysis and others is that this is unlikely to have a significant effect. Now, the water in the ground definitely has an effect. So if you go from being dry to being saturated, well, that will have a big effect on the heat transfer. But just typical rainfall percolating down through the soil, that doesn't transport a lot of energy. So there's anecdotal evidence for long-term temperature buildup in imbalanced systems, but there's not a lot of high-quality field data. So I think that's probably one of the reasons why different people have different opinions on it. But that's my opinion. It can be important in many cases. Okay, so we're going to talk about how we put the loads in, and they typically come from something like Energy Plus or eQuest or another hourly simulation tool. So an obvious question, why don't we use hourly loads? At the core of the simulation-based design tools is simulation of the ground heat exchanger, where we take the loads and all the ground properties and so on, we forecast over time what the temperature rise and fall is going to be. Right? And the reason we don't use hourly loads is because this simulation can take quite a while if we're using hourly loads, especially if we get out to 20 or 30 years. And the hourly simulation, it's not unusual to take 15 minutes or 30 minutes or 60 minutes. And we have to do this multiple times. This is this iterative process. So typically it might be 9 or 10 simulations. So if it takes 30 minutes, then you'd have to wait 4.5 hours for an answer. Right? Whereas the type of load representation we're talking about, this hybrid time step, these simulations can take a fraction of a second or a few seconds. So it's quite possible to do this either more or less instantly or in under a minute. Okay, in order to find that, we have what we call peak load analysis tool. This was developed originally by my student, then a master's student named James Cullen. He later did a PhD. We originally implemented this as a spreadsheet tool with the intention of integrating it into GLHEPRO. However, about 10 years later, it's still a standalone tool. Maybe that will change. But what the tool does is it takes 8,760. In other words, 1 day or 1 year's worth of hourly loads for heating and cooling. And from there, it finds the peak heating day and the peak cooling day. It lets the user then examine the testing of different peak load durations and in an attempt to establish how long the peak duration should be. So it calculates the normalized temperature response, and then it does it for both simulating an actual hourly load profile for that day and then a rectangular load profile. And then the user uses that to find the duration that most closely matches the temperature rise or fall, not of fall, but the temperature rise or fall over the day. We'll have an example later. Okay, we're going to pause there.